Welcome back, Cosmic Explorers. Caroline here. Imagine looking up at the night sky thousands of years ago, with no lights from cars or buildings, just a vast blanket of stars. The ancient Babylonians did this every night. But there was one light in the night sky that stood out from the rest, a bright, mysterious object that seemed to follow its own rules. This was the Star of Ishtar, or what we know today as the planet Venus. The Babylonians didn't know that Venus was another planet, similar to Earth in many ways. To them, it was a supernatural star in the heavens, and represented the goddess Ishtar. They told stories about her, such as her occasional disappearance to visit the underworld. But she would eventually return, bringing hope back to the land. This story of descent and return wasn't just a legend. It mirrored the real path of Venus in the sky. You see, Venus has a unique orbit that makes it disappear from view periodically. When it moves too close to the sun, Venus gets lost in the sun's brightness and is hidden from Earth for a while, like Ishtar journeying to the underworld. Then, after a few weeks, it reappears in the sky, a symbol of rebirth. How did the Babylonians realize that Venus wasn't just an ordinary star like all the others in the sky? They studied it carefully, night after night, year after year, keeping records of its every move. They noticed that, while other stars stayed in consistent, predictable patterns, Venus moved differently. Sometimes it appeared in the evening, sometimes in the morning, and sometimes it appeared to move backward from one night to the next. This wandering behavior showed the Babylonians that Venus had a special significance, different from any ordinary star. Today, we'll look at why planets seem to behave so differently in the night sky, and how ancient cultures tried to explain their behavior by creating different models of the solar system. The ancient Babylonians studied the cosmos by keeping very detailed records of the locations of every visible object in the night sky. Most of the bright stars they recorded moved in very stable, predictable patterns, but they also recognized 5 celestial bodies that moved differently. Today, we know these rule breakers as Mercury, Venus, Mars, Jupiter, and Saturn. What do these 5 objects have in common? They're all planets in our solar system. This record-keeping wasn't just an idle pastime. The ancient Babylonians believed that many of the objects in the sky, like Venus, were deities. So they connected their motion and behavior to events on Earth, such as war or famine. Many rulers would make decisions of state based on the predicted motion of the planets in the coming weeks or months. The knowledge gained by the Babylonians was passed down generation by generation. And nearly 1,000 years later, several Greek astronomers began wondering if this data could be used to construct a model of the universe. One early model of the universe was developed by the Greek philosopher Aristotle. His model was geocentric. Can you guess what that means? The prefix geo implies having to do with Earth, so geocentric means Earth-centered. Aristotle taught that Earth was in the center of the universe and everything orbited around it in circles. He considered the heavens to be perfect, and therefore was convinced everything in them must travel in perfect circles. Unfortunately, very little about Aristotle's model was correct, but it did generally explain the motion of objects through the sky and was accepted as fact for centuries. Its big weakness? Explaining the wandering motion of the planets. Based on Aristotle's geocentric model, the planets should have moved through the sky just like all the other stars, when clearly they did not. Around 500 years later, a mathematician from Alexandria named Ptolemy attempted to fix this flaw with Aristotle's model. He agreed with the geocentric nature of Aristotle's model, but added the idea that the 5 planets traveled on smaller epicycles, which are smaller circles that orbit around larger circles. He offered no explanation as to why they would undergo such a complex motion, but his model could be used to more accurately predict their location from night to night. It wasn't until the Renaissance, over 1,000 years later, that the geocentric model began to be seriously doubted by scientists. Now we know that it's the Sun at the center of our solar system, not Earth. It's the relative motion of Earth compared to the motion of the other planets in their own orbits that causes the wandering motion that has been observed for millennia. Let's find out why this happens. If you were to spot a planet, such as Jupiter, in the night sky, do you think its motion during the night would be different from that of the other stars? Over the course of a single night, nothing seems amiss. Just like stars, planets like Jupiter rise in the east and set in the west, following a predictable path across the night sky. But what if we came back outside tomorrow night and looked at Jupiter again? And what if we came back the next night? After several days, we would start to notice that Jupiter wasn't lined up with the same stars that it was lined up with a week ago. After a month, it would look like it was in a completely different part of the sky. What causes this? The difference comes down to distance and motion. Stars are incredibly far away, much farther than the objects in our own solar system. They're so distant that, even though they're moving at mind-boggling speeds, their positions relative to each other appear fixed to us. But planets are much closer to us. In fact, they're within our own solar system, orbiting the Sun just like Earth does. As they orbit, they move against the background of distant stars. This makes them appear to shift positions over time. Because each planet orbits at a different speed and distance from the Sun, we see them moving at different rates, sometimes speeding up, slowing down, and even appearing to reverse direction in what's called retrograde motion. For example, let's imagine that we view Jupiter in the night sky on a particular night and mark its location relative to other stars. A few weeks later, we view Jupiter again, but because both Earth and Jupiter have moved in their orbits, Jupiter now lines up with different stars. A few weeks later still, and Earth has now passed Jupiter in its orbit, so it actually looks like Jupiter has moved backward in the sky, even though it has continued moving forward in its own orbit. This is retrograde motion. It might continue to appear to be moving backwards for another month or two until the orbits align in such a way that it appears to be moving forward again, relative to other stars. So while distant stars appear to be part of a fixed, unchanging background, the planets in our solar system each have a unique path through the night sky. The ancient stargazers noticed this difference, and it led them to wonder, why do these few bright stars act differently? These questions sparked centuries of study, leading to our modern understanding of the solar system's layout and the unique, wandering nature of the planets. If you want to identify planets in the night sky, you could always look for this wandering motion yourself. However, that's going to take many stargazing nights to detect. Is there a way to look up into the night sky and immediately identify which objects are planets? In your lesson activities, you'll explore this very question. Without a telescope, it can be hard to tell for sure, but there are definitely some clues you'll learn to use. After completing this activity, I encourage you to go outside on a clear night and see if you can spot a planet in the sky. And for an extra challenge, see if you can tell which one you've found. As you do, remember the countless civilizations that have done this very activity throughout history, and marvel at how much we've learned about our universe since those early stargazers thousands of years ago. That's it for today, Cosmic Explorers. I'll see you next time as we continue our journey through this vast universe.
Hey, hey.